All right, our next concept really, it's not really a set of problems to be able to work. It's not like it's a derivative to find, but it's more of a concept to discuss. And there are going to be a few equivalencies we're going to develop that, as much as anything, are simply items to keep in mind moving forward later in this semester, and then also as you go into Calculus 2 and Calculus 3. So what I have here is a function. In the red, we have a function y equals f of x. We have a point in the domain x, and we have the point of tangency and the tangent line we've all sketched here. And so what I want to consider is, suppose we have this distance is delta x, all right? And then let's consider a few qualities we have here. I want to label some distances, and then we're going to see if we can discuss those. So we have x, we have this distance delta x, all right? Now what does delta x represent? It represents the change in x. As you move, if this distance is delta x, I'm going to erase this one, that distance is delta x. As you move from this point on the red curve to this point, that distance is delta x. It's the change in x from this point to that point. All right? Well, if you have a change in x from this point of tangency to this point here, you also have a change in the y coordinate. We've changed the x value from here across. This is the change in x. We also have the change in y. This vertical distance is the change in y. Now, as you move from this point to this point, that corresponds to the change in the y value. As you move from here to here, and in fact, I want to write this in this red color again. So this distance is delta x. This vertical distance is delta y. What does that correspond to? As you move from this point to this point, as we allow delta x to vary, then this point is the distance between x and x plus delta x. This is the change in the x value. This is the change in the y value on the red curve. Now, we also have another graph up here. We have this blue curve. And so the question now is, as you move from this point to this point on the blue curve, what values do we have? Well, that's also a change in x, and this distance going from here to here, this is also a change in y. All right? So the question is, what can we make of all this? Well, we have a little notational shift we want to have. Notice that this change, that distance, the change from this x value from this level to this level is different than the change from this point to this level to this level. On the red curve, the change in this case is much greater than the change on the blue line. Whereas when you go horizontally, notice the change on the red is equal to the change on the blue. So the change on the red is equal to the change on the blue here. But the y coordinates are different. As you move from x to x plus delta x, as you move this distance horizontally, the red curve changes quite a bit. The blue curve only changes a small amount. And so for that reason, this blue distance and this red distance are potentially different. And so we don't want to label this as also delta y, because then we have the same symbol representing potentially two different values. And so we introduce a new symbol, and that's really the point of this argument. One of the main points is we introduce a new symbol. This difference we call dy. dy is the change in the tangent line value. Delta y is the change in the function value. Now, we introduce the same notion on the horizontal scale. delta x represents the change in the function value, but dy represents the change in the blue tangent line value. But notice what's happening here. On the horizontal scale, delta x and dx, I've labeled this incorrectly, delta x and dx are equal to each other. That's one key here. Delta x and dx are always equal to each other on the horizontal scale. But what's different is the vertical. Delta y and dy are potentially different. But it should be clear this statement is true. These are not equal, but they are approximately equal. This distance and that distance are approximately equal. It's just in this particular case, it's a bad approximation. And this should sound familiar. How do we make the approximation better? As delta x gets smaller and smaller, notice again, delta x and dx are the same. But as those values get smaller and smaller, so as delta x gets smaller, dx also gets smaller. They vary equally because they're the same value. As delta x gets smaller and smaller, then this distance gets smaller. And now we're only talking about, let's say, this point. And now we're talking about that vertical distance. And now this little bit is dy, and this little bit is delta y, and they are approximately equal. The approximation has gotten much better. How can we make the approximation even better? We can let delta x get smaller. As delta x, which is the same thing as dx, as delta x gets smaller and smaller and smaller, this approximation gets better and better and better. And we will find out with our work later on, as we take the limit, in the limiting value as delta x goes to 0, these values in the limit do become equal. And so we have a couple statements here. Delta x is equal to dx, delta y is approximately equal to dy. Now, the next little piece is this. What do we mean by this expression? Well, I want the slope of the tangent line evaluated at this value of x. Right? Well, I know the slope of the tangent line. I know the slope of this blue line. The blue line is the rise over the run. I know what this is precisely equal to. It's equal to the rise over the run. And we also have that the slope of this blue line is approximately equal to the slope of that secant line. What is the slope of the secant line? The slope of the secant line is delta y over delta x. These are approximately equal. These are equal. Now, from that half of this statement, we can multiply both sides of the equation by dy, and what we have is this. Multiply both sides of the equation by dx. dy is equal to f prime of x dx. We will use that statement over and over and over and over again in Calculus 2, Calculus 3, and when you go to differential equations, that gets used over and over again. But what we also have is this. F prime of x, with this half of the equation, this is now an approximate equation, multiply both sides of that expression by delta x, and we have, let me rewrite that better. We have that delta y is approximately equal to f prime of x delta x. And when we do things later on like constructing Riemann sums and doing limits of Riemann sums, that approximation is going to come into play. None of this is something that you need to be able to apply to a problem and be able to get an answer. None of this is something you need to be able to reproduce. It is more an idea, and the two basic takeaways are these two main statements, and I'll put them up here. The two main takeaways are dy is equal to f prime of x dx, and delta y is approximately equal to, and as delta x gets smaller and smaller and smaller, this approximation gets better and better and better, because as delta x gets smaller, well, delta x is always equal to dx. So these denominators are always equal to each other. But as delta x gets smaller and smaller, these numerators get closer and closer to each other. And so as delta x gets smaller, this approximation gets better, which means this approximation gets better, which means this approximation gets better. As delta x gets smaller and smaller, this approximation gets better. And what we'll do is we will use this later on when we construct Riemann sums and do limits of Riemann sums. And then this expression gets used when we talk about definite integrals and integral computation later on. So these are the two main takeaways. This is all theoretical work. None of this is a practical, be able to do a problem kind of thing. All of this is some information, and later on when we make substitution of this for this, or this for this is the rationale as to why that is permitted. It's a discussion of the differentials and the relationships they have to the slopes of the tangent line and the functions themselves.